I want to introduce now the Dirac delta function, delta x. It's a generalized function that we can't define its value everywhere, but we can say what properties it has. And the particular property it has is that it's 0 everywhere except the origin, but the integral of this function is always equal to 1. Now we can imagine it as the limit of a top hat function as the width, b, tends towards 0, but the area remains constant, which means the height must tend towards 1 on b, which obviously is infinite. Now, the properties of the delta function are really useful in Fourier analysis, as we'll see. The next couple of slides, I'm just going to look at some of the properties that the delta function has and the way it behaves when you use it in integrals. So the first example is if we have the delta function, we multiply it by some other function of x, and we integrate from negative to positive infinity, then what we can say is that because this function delta x is 0 everywhere except for x equal to 0, we can replace f of x with f of 0. So if we do that, we can pull f of 0 out of the integral, which makes the integral look like this. Now we're integrating delta x over all of x, but we know this integral is equal to 1 because that's really the definition of a delta function, which means we just get f of 0. So in other words, integrating delta x f of x selects out the value f of 0. So it's a sifting function, if you like. It's often referred to as a sifting function. You can generalize this if you offset the delta function by some offset x naught and integrate, then you select out the value x naught. So offsetting the delta function allows you to pick out any value f of x naught. Here are a few other properties of the delta function. This is by no means an exhaustive list, just some of the ones that may come in useful. Delta x is an even function, so delta x is equal to delta minus x. You can scale the delta function. If you put a scaling factor a in here, then this is equal to delta x divided by the absolute value of a, which is kind of saying that scaling the width of this infinitely narrow function changes the width and therefore the area. So if you make a something which is bigger than 1, you make it narrower and you divide the width when you integrate this by a factor of a. You can also look at the derivatives of the delta function, and you can integrate over the derivative of the delta function, and that selects out, in this case, the negative of the derivative of your function f of x. There are also relationships for higher order derivatives of the delta function, which I'm not going to include here. The final property I'll put on this page is the sifting function again. That is, if you integrate some function f of x with an offset delta function, x delta of x minus x naught, then you get back the value of the function f of x naught. We've already seen this one, but it's so useful and important it's good to have it twice. The delta function sifts f of x when it's integrated and returns a single value of f of x naught. And this is a property that we're going to use over and over again.